Hello, my name is David O'Connor from the Department of Chemistry and the ERI, and I'll be talking to you today about my PhD, which is on primary biological aerosol particles known as PBAP. Basically, what they are, how we sample them, and their contribution to ambient air pollution. Obviously, I didn't do all this work by myself, so I'd like to thank all these people that have helped me thus far on my PhD, and the EPA for funding me, and especially to my supervisor, Professor John Sotto. So what are primary biological aerosol particles, or PBAP as I'll be referring to them from now on? Here is my aforementioned supervisor asking that very same question. Some of the main classes of PBAP include pollen, fungal spores, bacteria and viruses. They come in a variety of sizes and shapes. Some can be very spherical, like the pollens you can see in the figure, or some can be rod-shaped, like the bacteria you can see. But as an atmospheric chemist, I like to categorize particles by their size. The fine fraction of PM 2.5 refers to particles between 0.1 micron and 2.5 microns. In the graph shown here, we can see the chemical composition of PM 2.5 for the UK. You can see that it's dominated by organic carbon, and interestingly, this is where PBAP contribute. PBAP such as fungal spores, bacteria, and subpollen are all seen in this region. When I refer to subpollen, I'm talking about pollen which is being broken down and degraded in the atmosphere. And it has been seen that PBAP contribute between 4 and 11% of the total mass in this size fraction. Moving to the coarse fraction, that's basically particles between 2.5 and 10 microns. We see that the contribution from PBAP in tropical and rural areas increases to 1 to 18% of the total mass, while in urban centres such as Vienna, it can be seen to be between 1 and 7% of the total mass. And this is due to increased contributions from anthropogenic sources. Moving to the ultra-coarse, a term not used very often in atmospheric chemistry, and it refers to particles greater than 10 microns. In the figure we can see a whole host of pollens and their sizes, and we can see that they vary from 15 microns to 70 microns. So now that we know what PBAP are, how are they sampled? Well, the most traditional techniques use simple impactors. The instrument which we use in our research is a spore watch, and it's seen in the top corner here. It basically sucks in the ambient air at 10 litres per minute onto a suitable substrate. In our case, we use an adhesive silicone tape. This tape is then brought back to the lab and analysed under a light microscope. And we get images, as we see here, of alder pollen. This is obviously very laborious and requires skilled personnel to undertake, which makes it very difficult for analysis. Also, the time resolution for the spore watch isn't very good. So Scott's thinking with our research, is there any other possible ways of categorizing PBAP? And there is. Fluorescence is a known property of PBAP due to the biofluorophores contained within most PBAP, such as tryptophan, NADH, and the flavonoids, just to name a few. So this got us interested to see whether fluorescence could be used to determine different PBAP species. So using a normal fluorescence spectrometer, we took the fluorescence spectra of 2 grass species and saw that they had chlorophyll B peak at 680 nanometers in common. Moving to the conifers, we see that they also have very similar fluorescence spectra, but quite different to that seen from the grasses. So now that we knew that fluorescence was able to determine the difference between different PBAP species, we were interested to see whether there was an instrument able to do this out in the field. And there is. The WIB-spore uses fluorescence to determine the difference between biological particles and other chemical species present in the ambient environment. It does so through the use of 2 xenon flash lamps tuned to 280 and 370 nanometers, which are the excitation maxima for tryptophan and NADH. Should a particle show fluorescence, it is deemed to be biological. The WIB-spore also incorporates a diode laser at 635 nanometers, which is used to size and shape the particle. It essentially can tell the difference between a spherical and rod-like particle. The time resolution for the WIB-spore instrument is very high, in the order of seconds to milliseconds. Moving on to the schematic of the WIBS instrument, a single particle comes in, it hits the diode laser, it's sized and shaped, it moves on to the first xenon flash lamp to evaluate its fluorescence characteristics, onto the second xenon flash lamp at 370 nanometers to evaluate its fluorescent characteristics at this wavelength and on, and then the whole process occurs again for the next particle. We placed this WIB-spore instrument and spore watch along with a weather station down in Killarney National Park on February and March 2010. And here we show some of the results which we obtained from this campaign. The yellow peaks indicate total particles seen for the days for which we were down for this campaign, and the red peaks show peaks for large fluorescent particles during this campaign. As you can see, the large fluorescent particles peak around midday, while we see very few particles, if any at all, at night time. The large red peak indicates possibly a pollination event, while the sudden spike in total particle count was determined after analysis to be construction occurring next to our sampling site. As you can see, over 100,000 particles were analysed during this campaign, so we needed a varied way to filter the data. Things like filtering the data due to its fluorescence, its size and its shape, or normalising the fluorescence data to size and shape were used during the analysis. And here I've just highlighted what we've deemed to be pollination events throughout the campaign. I'll be focusing on events 1 and 2 because once you've seen one pollen event, you've seen them all. The WIBs for instrument determined that the pollination event number 1 occurred at 10:58 and 12 seconds and finished at 17:55, 54 seconds. When we correlated this data back to the spore watch, we saw that it correlated very, very well, as can be seen in the graph. And this peak was generally hue, although there was some hazel involved. Moving to the pollination event number 2 on the 28th of the 2nd, 2010. This peak, the WIBs was determined by the WIBs to start at 11:44 and 49 seconds and finishing at 16:26 and 55 seconds. And again, when we brought this back to the spore watch data, it agreed very, very well with it. And this is mainly a hue pollen event. So through these two events, we were able to determine statistical values which the WIBs used to determine what was a hue pollen. It showed that the average size for the hue was around 27 microns, and it was very, very spherical. This is very good, however, it's of no use unless it corresponds to previously cited literature on what a hue pollen should look like. And in literature, hue pollen is seen to be 27 microns in diameter, and as we can see from the images, very, very spherical. And in conclusion, 1. The WIB-spore instrument determined the diameter of the hue pollen in flight to be 27 microns, and to be very spherical. 2. It was able to determine the total number of particles during the Killarney National Park campaign. And 3. It was able to determine the meteorological parameters which best suited pollinaries during the campaign. This is of great interest to people who are interested in climate change and also to people who are affected by hay fever. Thank you very much for watching.